So we're talking about the uniform circular motion for the first chapter. And the object is moving at constant speed. Can you tell me whether it's moving at constant velocity? No. Why it's not moving at constant velocity? Yeah, because in a circular motion, the direction of the motion is keep changing. So the velocity is not constant. We say because the direction of motion is changing. So therefore, the object is not moving at constant velocity. And because the object is not moving at constant velocity, so there will be acceleration. Yeah. If you still remember for the acceleration, the definition of acceleration is change in velocity over change in time. So whenever the velocity is not constant, that means there's a change. Then there will be acceleration. Now, in terms of circular motion, we have to introduce other quantities to describe the motions. So I think it's more natural for us to use the angle instead of the distance. Is it? For a circular motion. Now, let me draw a perfect circle. Perfect circle. So do you think it's more natural to use the angle instead of the distance to describe the position of the object? So this is the angle. Then it's more easier to recognize the location using angle. So we have one term we call the angular displacement. So that is an angle. You may say that is angle traveled by the object. Now the unit we use for angular displacement is not degree. We use radian. Have you ever learned about the radian in core math? I just want to remind you, okay? Let's say 360 degrees, how many radian? 2 pi radian. Now you need to know how to convert it, but most likely in the question, you just stick with the unit radian. So this is the first quantity we need to use. So this quantity tells us the position or the change in position of the object. And then the second one, we want to know how fast the angle changes. So we have another term, we call the angular speed or angular velocity. In your syllabus, you don't need to know the differences between these two quantities. Actually, one is vector, another one is scalar. But you don't need to know about the direction of the vector angular velocity. You just need to know how to find their values. That's enough. So we define it as the rates of change in angular displacement. So that means that is how fast the angle changes. Now in formula, for angular velocity, we use the symbol omega. Omega. It looks like a W, but it's a bit fat here. 你笑乜嘢？你個腦 Okay. I think you have seen another omega. There's a capital letter. So, but we use that one, okay? So for in terms of the formula, you may write the angular velocity omega equal to change in angle. That means a change in angular displacement over change in time. So that is the definition of the angular velocity. Now then we can take a look at some, we can also write it in terms of another formula. So if the object have complete one circle, then the angular displacement will be 2 pi radian. The time, we call it the period. So that's another formula for us to find the angular speed or angular velocity of the object. So let's take a look at two very common angular velocity that you need to use in the exam. How long does it take for the Earth orbit around the Sun for one circle? For one circle? 1 year. Then we can find the angular speed for that. So for one circle, one complete circle. So let's say if you're talking about the Earth orbiting around the Sun, then the angular speed will be 2 pi over 1 year. Remember, you need to convert the year to second. The SI unit for angular speed should be, so this one, the unit should be radian per second. Okay, radian per second. Not difficult at all, is it? So, and then you need to convert the year to second. So you just consider the 365 days times 24 hours times 60 times 60. Okay. Then just make use of your calculator. But the value is pretty small. So the value is around 1.99 times 10 to the power -7 radian per second. Another period that you may know, you should have known, is the self-rotation of the Earth about its rotation axis. How long does it take? 24 hours or 1 day. So there will be 2 pi over 1 day, and then you need to know, convert the 1 day to second, right? Now we will go to use these two values later on. We're going to use these two values later on.哦，你幾點翻嚟啊？OK。Simple。係。Let's move on now. Now just let's think about a circle. Let's say the object moved from this point to this point. I think it's quite natural or quite simple to imagine that there should be some relation between the speed and the angular speed. Hello. I think it's quite natural for us to actually we can relate the angular speed and the speed together. There's one formula relating the speed and angular speed. So let's say for you know how to define the speed. The speed is defined as a distance over time. Now you have learned this formula in math already. So the del theta is change in angle, or you say that is the angle displacement. How about how to relate the distance s with the angle displacement and the radius? Yeah, using the formula of the arc length. So the distance traveled is the s and then divided by the time. The distance traveled, you can use the formula of the arc length. Do you still remember it? Remember 咁係咪 ？You know about it 㗎嘛？You need paper, you can take it here. Now this one is actually how we define angular speed. So that's why we can rewrite the formula. The speed equal to the radius times the angular speed. Okay, this is the first formula that you need to remember. V is the speed. Or you say the velocity. Now, I just want to remind you once again, in GCE level, although there's a formula sheet given to you, but that is only one page formula sheet. Not all the formulas are included. For almost all the formulas, you need to remember it by yourself. Okay. 做什麼? And so if you still remember, the angular speed can be written as 2 pi over period. So you may consider this another formula. The angular speed is 2 pi over period. I think it's not difficult to understand 2 pi over period. Because 2 pi r is the circumference of a circle. That means the distance traveled by object in one period. Then divide by that time period. Then you get a speed. Okay. Now let's get some interesting question. Now this is the Earth. This is the Earth. Now here is the equator. Do you all know about the equator? Do you know? Equator. I don't know how to explain it. You know about it. 赤道. Now, how can I explain it in terms of now in terms of physics, how to explain the equator, right? Yeah, you may say that is the middle. Now, this is the rotation axis of the Earth. The Earth rotates around about this axis. Where is the North Pole? Sorry, never mind. So there is some polar bear. A good drawing. Okay. Here is some penguin. Okay. Penguin. I'm very good at drawing penguin. So let's consider two men. So let's say one guy is standing above the equator. So let's say another one. June go back to Japan. So let's say this angle is 30 degrees. Do you think there is some differences between their speed? You may consider when you rotate this sphere, June is rotating about this axis, this circle, all right? But Elson is rotating about this circle. So they have different speed because they have different radius of circle. They have different radius, but they have the same angular speed. They have the same angular speed. So then how can I find the speed of June and Elston? So let's find it. Now we just apply this formula. But one thing we also need to use is the radius of the Earth. Radius of the Earth. We use this value very often. So it's around 6,378 kilometers. So that is the radius of the Earth. So let's find the speed of Elson. Now then you use 6,378. Now remember, change it back to meter, right? Now no one will remind you in NFO. Almost all the question you need to change, let's say km to meter, not meter to meter, and so on. But then you need to use the angular velocity you find it before, 7.27 times 10 to the power -5. Then you get the speed of Elson. Indeed, this speed is quite large compared to almost all the transportation. Yeah, we don't feel anything. Do you think DC when you are orbiting around the equator? No, because you have get used to it already. Yeah, the speed is faster than an aeroplane. It's faster. It's larger than speed of light, speed of sound, is it? It's larger than speed of sound. But the aeroplane is actually moving relative to you or relative to the ground. Hello. Enough. Don't need to. Let's take a look at June now. Now the radius of June is different. Huh? So what should be the radius of the June? Times cosine 30 degrees, am I? Do you see this do you see this triangle? The hypotenuse is the radius of the Earth. And then this angle is also 30 degrees, right? Okay. Any question? No. Hypotenuse. This is the hypotenuse. This is the hypotenuse. This is hypotenuse. This one is the radius of the Earth. Then times cosine 30 degrees, then you get a radius of June. And then times the same angular speed. June is moving slower than June is moving slower than Elson. The speed of the June is around 602 meters per second. 402 meters per second. How about the penguin or the polar bear? What is their speed orbiting around the Earth? Zero. That's zero. If they're exactly located at the North Pole, then the radius will be zero. It just seems like they are rotating by themselves one circle in one day. The speed is zero, but because the radius is zero. Okay, so we have talked about this example. Then let's move on. Now maybe let's talk about another example also. Let's say, I will skip that one. Now we have relate the speed and angular speed together. Then we're going on to take a look at the acceleration. Take a look at the acceleration in a circular motion. Now we talk about that because the velocity is changing. So there is change in velocity. Therefore, there is an acceleration in a circular motion. Then actually we want to find a formula for the acceleration. Now let's draw a circle here. Okay. Oh, perfect. So there's two points. So let's say the object is moving from point A to point B. Now they have the same velocity. Sorry, they're moving at constant speed. But the magnitude of the velocity is constant, but the direction is not. There's a change in the direction of the velocity. And if you cannot understand the proof, that's okay. You don't need to know the proof. You just need to know about the result, the formula. But I still need to show you how to prove it. So first of all, we need to find a change in velocity. So that will be the VB minus VA. That is the final velocity minus the initial velocity. Right? And then we need to draw a vector diagram. Have you learned about the vector subtraction in core math? No. Yeah, you did. Yeah, you have learned about it, lah. Whatever lah, you have learned it. Then you have learned it. Now then I'll always like to do the addition instead of the subtraction. You know negative a vector, that means you just reverse its direction. Then remember, have to tell, have to tell. When you do an addition of two vectors, remember how to tell. Hmm? That's why you need to ask. So this one is a change in velocity. Well, you can see how. Now then you can see how we draw the change in velocity. Oh, sorry. Just take a look at it is okay. If I draw in this diagram, but somehow we can show that the change in velocity is towards the center of circle. That's the direction. Now the most interesting part is that this angle is delta theta. It's a bit difficult to show it. Now you extend the VA, extend the VB, and then this angle will be delta theta. I'm not sure if you can see it. I'll just show you a bit. This is 90 degrees, this is 90 degrees. Then this angle, it should be 180 degrees minus delta theta. So, and never mind. And so therefore this angle is changing delta theta. I can't enlarge it. Now this one is delta theta. This is 90 degrees. This is 90 degrees. You can see this is a quadrilateral. So this angle sum of a quadrilateral is 360 degrees. So therefore this angle should be 180 minus delta theta. So therefore this angle is delta theta. Then this angle is angle between the VA and VB. That's why in the diagram it's delta theta. Oh. Next. Now we will take the angle theta. But the magnitude of VA and VB is the same because we are talking about a constant speed motion. And then for the acceleration, you know, it's finding the change in velocity over change in time. That means we need to find the magnitude of a change in velocity. Okay. Then how can we find it? It involves a bit math. Now we take the change in time very small or 10 to 0. At that point, okay, B is very close to A. Or the angle theta is very close to 0. Okay. Well, now, at that time, the angle theta is close to 0. Oh. Now then you can see, okay, then we can consider this triangle very thin, very sharp, and it can kill people. And this one is very sharp. And then, so therefore, now then there's a physics trick. There's a very thin. There's a change in theta. Then this length is V. This length is also V. Very small. Just remember very small. Very small. Then you may consider if the angle is very small, then it's very close to 0. If the time is very small, then it's very close to 0 嘛，係咪？ The angle is very close to 0. And then at that time, we can consider this as a theta of a triangle. Theta, do you know what is theta? Not the website. That's a theta. Then this arc length is you may consider this arc length will be like the change in velocity. And remember how we find the arc length of a triangle. We use the radius times the angle. So that's V times the delta theta. Hold on, we almost get it. After we've done it, let's take a 5 minutes break. I think we can finish this chapter today. Now we can rewrite this form. Then you can see that A will be V times the delta theta over change in time. And that is the angular speed. This one is the angular speed. The angular speed can also be written as V over R. You learn it? You just have this formula before. And then by substitute the omega V as V over R, then you get V squared over R. Or if you substitute the V in the formula, then you get R omega squared. Okay. In total, there are 3 different forms for the assertion. In general, we just use this one or this one. We seldom use this one. We seldom use V omega, the first one. Oh, done. Now, you need to remember the formula. That is the assertion for a circular motion. Now, it's either V squared over R or R omega squared. Whenever you see that the motion is a circular motion, you always need to use it. Use this formula. It's a must. This formula is 100%. You need to use it 100% if the question is about circular motion. No, don't ask me whether angular speed will be given. If given you all other things, then you find the angular speed. If you're given the angular speed, you may find the radius. Vice versa. Now, because you can see that the change in velocity points towards the center of circle. So for this assertion, we have a special name for it. Now, this assertion is always pointing towards the center of circle. So therefore, we have another name for the assertion. We will call it centripetal assertion. This one means center, this one means towards. That means towards center. That's a name for the assertion in a circular motion. Well, let's take a 5 minutes break.